Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where in the quiet depths of space, new stars are born from whispers of gas and dust, like soft breath condensing on a cold window. Matter gathers in the darkness, slowly, patiently, following ancient rhythms that have played out for billions of years across our universe. In the gentle embrace of the cosmos tonight, we'll explore one of nature's most beautiful mysteries: how stars form from the seemingly empty void. This is not a violent process, despite what dramatic documentaries might suggest. Instead, it's a patient dance of physics, unfolding over millions of years with the grace of a flower blooming in slow motion. As we begin our peaceful journey through stellar nurseries, imagine yourself floating weightlessly among the cosmic clouds, where baby stars take their first breath. Here, in temperatures colder than Antarctic winter, yet warmer than absolute zero, matter moves with purpose, drawn together by forces so gentle they're barely perceptible, yet so persistent they can build suns. The story of star formation is ultimately our story too. Every atom in your body, save for the lightest hydrogen, was forged in the nuclear heart of a star that lived and died before our sun was born. Tonight, as you drift towards sleep, we'll trace that ancient legacy, following the cosmic pathway from empty space to shining star, from stellar death to new life. In an endless cycle that connects us all to the stars above, let's begin our exploration in the vast, seemingly empty regions between existing stars, where the universe keeps its most profound secrets hidden in plain sight. These are the molecular clouds, the stellar nurseries, where tomorrow's suns wait patiently to be born. In the quiet space of interstellar regions, where the density of matter is so low that every cubic centimeter contains fewer particles than the best vacuum we can create on Earth, something magical happens. Here, in this cosmic near-emptiness, gravity begins its patient work, drawing together the sparse atoms and molecules that drift through the galactic medium. Like cosmic snow. These molecular clouds, as astronomers call them, are vast beyond human comprehension. Some stretch across hundreds of light years, distances so large that light itself, traveling at 186,000 miles per second, takes centuries to cross from one edge to the other. Yet despite their enormous size, these clouds are extraordinarily tenuous, containing perhaps a few hundred to 1,000 particles per cubic centimeter, making them far more empty than any space we experience on Earth. Gently, we discover that these clouds are not uniform blankets of gas and dust. Instead, they have structure, wispy filaments, and denser cores, like the delicate patterns frost makes on a window pane. Within these structures, gravity works with infinite patience, slowly increasing the density of matter grain by grain, molecule by molecule, over time scales that dwarf human civilization. The temperature in these stellar nurseries hovers around 10 to 20 degrees above absolute zero, cold enough that most gases would freeze solid on Earth, yet warm enough to allow the gentle motion needed for gravitational collapse. This temperature is maintained by a delicate balance. Cosmic rays and starlight provide just enough energy to keep the gas from cooling further, while the expansion of the universe and radiation into space prevent it from warming significantly. As our journey continues deeper into these cosmic cradles, we encounter the fundamental physics that governs star formation. Sir James Jeans, a British astronomer and physicist, first described the conditions needed for a cloud of gas to collapse under its own gravity. The Jeans criterion, as it's known, tells us that a cloud will begin to contract when its gravitational attraction overcomes the outward pressure of its internal motion and heat. This balance is exquisitely sensitive. A cloud that's too hot or too small will disperse into space, its particles flying apart faster than gravity can pull them together. But when conditions are just right, when the cloud is cool enough and massive enough, gravity wins and the slow, gentle collapse begins. The critical mass needed for this collapse is enormous by earthly standards, typically requiring a cloud to contain at least 10 to 100 times the mass of our Sun. Yet in the vast scale of galaxies, where hundreds of billions of stars shine, such massive clouds are common, drifting through space like cosmic seeds waiting for the right moment to sprout. Let's drift into the heart of a collapsing molecular cloud, where gravity's gentle pull grows stronger with each passing millennium. As the cloud contracts, its gravitational field intensifies, pulling in more material from the surrounding region. This process feeds on itself. The more matter that falls inward, the stronger the gravitational attraction becomes, drawing in even more material. But this collapse is not uniform or simple. The cloud fragments into smaller pieces, each following its own gravitational destiny. Some fragments become individual stars, while others break apart further, creating binary or multiple star systems. The largest fragments may become massive stars that burn bright and brief, while the smallest barely gather enough mass to ignite nuclear fusion, becoming the dim red dwarf stars that will outlive all others. Within each fragment, matter spirals inward like water flowing down a cosmic drain, but infinitely more slowly. The conservation of angular momentum, the same physics that makes figure skaters spin faster when they pull in their arms, causes the collapsing cloud to rotate more rapidly as it shrinks. This rotation flattens the cloud into a disk, with the densest material settling toward the center. Now we float toward the very heart of this process, where temperature and pressure begin their inexorable rise. As the cloud contracts, gravitational potential energy converts to heat, warming the gas degree by degree. This warming creates pressure that tries to halt the collapse, leading to a delicate dance between gravity pulling inward and pressure pushing outward. For millions of years, this balance shifts slowly in gravity's favor. The cloud continues to contract, its temperature rising gradually from the frigid depths of space toward the warmth needed to kindle a star. Throughout this process, the matter behaves like a gentle giant, moving with stately grace despite containing the mass of multiple suns. The rotation of the collapsing cloud creates fascinating structures. Material near the poles falls inward relatively directly, but matter in the equatorial regions must first spiral inward through the growing disk. This disk becomes a cosmic record player, with different regions rotating at different speeds according to Kepler's laws, the same physics that governs planetary orbits. As the central density increases, something remarkable happens. The core begins to decouple from the outer regions of the cloud, while the envelope continues its leisurely collapse over millions of years. The innermost region, now only a few times larger than our solar system, begins a more rapid contraction. This marks the birth of what astronomers call a protostar. Like whispers in the night, the protostar announces its presence through infrared radiation. Still far too cool to shine in visible light, it glows warmly in the infrared, fed by the steady rain of matter falling onto its surface. This accretion releases gravitational energy, heating the growing object and making it visible to our infrared telescopes as a faint, warm beacon in the cosmic dark. The surrounding disk continues to feed the protostar, channeling matter inward through viscous processes we're still working to understand. Magnetic fields threading through the disk may play a crucial role, creating friction and turbulence that allows material to lose angular momentum and spiral inward. These same magnetic fields may also launch powerful jets of material from the protostar's poles, carrying away excess angular momentum and helping to regulate the accretion process. In the quiet space of this stellar cocoon, complex chemistry unfolds. The warmth of the growing protostar begins to evaporate ices and drive chemical reactions in the surrounding disk. Water, carbon monoxide, and other simple molecules that were frozen onto dust grains begin to return to the gas phase, creating the raw materials that may someday form planets. Gently, we discover that the story of star formation cannot be told without understanding the crucial role of dust, tiny solid particles no larger than the smoke from a candle, yet essential to the birth of stars. These microscopic grains, composed of silicates, carbon compounds, and ices, serve as both the building blocks of future worlds and the cosmic thermostats that regulate stellar birth. In the frigid depths of molecular clouds, dust grains provide surfaces where gas molecules can meet and stick together, forming more complex compounds. Like cosmic matchmakers, these grains facilitate chemical reactions that would be impossible in the sparse gas alone. Hydrogen atoms landing on grain surfaces can find each other and combine to form molecular hydrogen, the most abundant molecule in the universe, and the primary constituent of star-forming clouds. As our journey continues through these stellar nurseries, we observe how dust grains themselves evolve. They grow by accretion, gathering mantles of ice and organic compounds as they drift through the cloud. Water ice is the most abundant of these frozen coatings, but methane, ammonia, carbon monoxide, and more complex organic molecules also contribute to these cosmic snowballs. The presence of dust dramatically affects the thermal behavior of molecular clouds. While gas molecules can radiate energy into space through atomic and molecular transitions, dust grains are far more efficient at absorbing and re-emitting radiation. This makes dust-rich regions particularly effective at cooling, allowing them to reach the low temperatures necessary for gravitational collapse. Let's drift into the heart of this cosmic chemistry lab, where dust grains serve as tiny factories for molecular production. The surfaces of these grains are cold enough that even hydrogen atoms stick when they land, giving them time to meet other atoms and form bonds. Over millions of years, this process builds up complex organic molecules, the same carbon-based compounds that form the basis of life on Earth. When a molecular cloud begins to collapse and form a protostar, the fate of its dust depends critically on distance from the growing star. In the outer regions, where temperatures remain low, dust grains continue to grow and evolve, potentially forming the seeds of future planets. But closer to the protostar, where temperatures rise above the freezing point of water, the grain mantles begin to evaporate, returning their molecular cargo to the gas phase. Now we float toward regions where this sublimation process creates beautiful complexity. As water, carbon monoxide, and other ices evaporate from grain surfaces at different temperatures, they create chemical gradients in the protostellar disk. These gradients may determine where different types of planets can form, rocky worlds in the warm inner regions, gas giants beyond the water ice line, and exotic compositions in the frigid outer reaches. The dust itself tells a story written in starlight and stellar winds. Observations with infrared telescopes reveal the telltale signatures of different grain compositions and sizes. Silicate dust produces characteristic absorption features in the infrared spectrum, while carbonaceous grains and ice mantles each contribute their own spectral fingerprints. By analyzing these signatures, astronomers can map the distribution of dust throughout star-forming regions and trace how it evolves during the stellar birth process. In the quiet space of protostellar disks, dust grains begin a new phase of their existence. No longer merely drifting through space, they now orbit the growing star in ordered paths, subject to the competing influences of stellar radiation, gravity, and gas drag. The smallest grains are easily blown away by radiation pressure, while the largest are too massive to be significantly affected. This creates a natural sorting process that may be crucial for planet formation. Magnetic fields add another layer of complexity to the dust story. Charged particles in the gas are tied to magnetic field lines, but dust grains, being electrically neutral, can drift across these fields. This differential motion between gas and dust creates friction and affects the dynamics of cloud collapse and disk evolution. Understanding these magnetized processes is one of the cutting-edge frontiers in star formation research. As the protostar continues to grow and heat up, it begins to clear away the dust in its immediate vicinity. Stellar winds and radiation pressure combine to create cavities in the surrounding cloud, allowing us to glimpse the newborn star for the first time in visible light. These clearings expand slowly outward, eventually dispersing the entire birth cloud and revealing the completed stellar system. Gently, we discover that some dust survives this violent clearing process. The grains that remain in the protostellar disk may aggregate into larger bodies, first pebbles, then rocks, then asteroids, and eventually planets. This process of dust aggregation is still poorly understood, representing one of the major unsolved puzzles in our understanding of how solar systems form. The chemical composition of surviving dust grains preserves a record of conditions in the early solar system. Meteorites that fall to Earth contain pristine samples of these primordial materials, including polymer grains that formed around other stars, before being incorporated into our own solar system. These ancient messengers tell us about stellar nucleosynthesis, the chemical evolution of galaxies, and the processes that led to our own existence. Like whispers in the night, dust grains carry messages across vast distances and enormous spans of time. They connect the death of ancient stars to the birth of new ones, the formation of planets to the emergence of life. and the local processes in our solar system to the grand cycles of galactic evolution. In their microscopic structures, we read the history of the cosmos itself. The study of dust in star-forming regions has been revolutionized by space-based infrared telescopes that can peer through the obscuring veils of these cosmic nurseries. The Spitzer Space Telescope, the Herschel Space Observatory, and more recently the James Webb Space Telescope have revealed unprecedented detail in the structure and composition of stellar birth sites. These observations show us that star formation is far more complex and beautiful than we ever imagined. As our journey continues through the dusty realm of stellar nurseries, we begin to appreciate how this seemingly mundane component of the cosmos plays such a crucial role in the grand story of star and planet formation. Without dust, molecular clouds would be unable to cool to the low temperatures needed for collapse. Without dust, the complex chemistry that creates organic molecules would not occur. Without dust, planets like Earth could never form, and life as we know it would be impossible. As our journey continues deeper into the heart of stellar birth, we encounter the protostar, a cosmic embryo slowly awakening in its dusty cocoon. This is not yet a true star, for nuclear fusion has not begun in its core, but it is no longer merely a collapsing cloud. Instead, it occupies a middle ground, a gentle transition between the diffuse matter of space and the concentrated energy of a mature star. The protostar grows through accretion, fed by a steady diet of gas and dust spiraling inward from the surrounding disk. This process is remarkably gentle, despite involving energies that dwarf anything we experience on Earth. Matter falls toward the protostar's surface at speeds of several kilometers per second, fast by human standards, but leisurely compared to the speed of light that will soon carry energy outward from the star's nuclear core. In the quiet space of the protostellar cocoon, temperatures slowly rise as gravitational potential energy converts to heat. The protostar's surface temperature may reach a few thousand degrees, hot enough to glow red-hot, like a piece of metal in a furnace, yet still far cooler than the sun's surface. This warmth begins to drive away the surrounding gas and dust, creating the first tentative clearings in the birth cloud. Let's drift into the structure of the growing protostar itself, where pressure and temperature increase steadily toward the center. Unlike a mature star, which maintains a delicate balance between gravitational collapse and radiation pressure, the protostar continues to contract slowly, its interior growing ever denser and hotter. This contraction will continue for millions of years, until the core becomes hot and dense enough to ignite nuclear fusion. The protostar's evolution follows well-understood principles of stellar structure, but with the added complexity of continued mass accretion from the surrounding disk. As more material falls onto the surface, it releases gravitational energy that heats both the accreted material and the protostar's interior. This process is self-regulating if accretion proceeds too rapidly. The resulting luminosity can drive away the infalling material, while too little accretion fails to provide the energy needed to support the protostar against gravitational collapse. Now we float toward the fascinating dynamics of the accretion disk that feeds the growing protostar. This disk is not a simple, uniform structure, but rather a complex system with its own physics and evolution. Viscosity within the disk causes material to spiral inward while angular momentum is transported outward, allowing the disk to spread while its inner regions feed the central object. The source of this viscosity has long been a puzzle in astrophysics. The disk material is too sparse for ordinary fluid viscosity to be significant, yet observations clearly show that material does spiral inward. The most likely explanation involves magnetorotational instability, a process where magnetic fields threading through the disk create turbulence. That acts like an effective viscosity, stirring the disk and allowing accretion to proceed. Gently, we discover that protostars are not quiet objects. Despite their peaceful growth over millions of years, they launch powerful jets of material from their polar regions, streams of gas moving at hundreds of kilometers per second that can extend for light years into space. These jets are among the most dramatic manifestations of star formation, yet they serve a crucial regulatory function, carrying away excess angular momentum and preventing the protostar from spinning itself apart. The launching mechanism for these jets involves the complex interaction between the protostar's magnetic field and the inner edge of the accretion disk. Magnetic field lines threading through the disk can become twisted by the disk's rotation, creating a magnetic pressure that accelerates material away from the system. This process is similar to the mechanism that powers jets from supermassive black holes, but on a much smaller and gentler scale. As the jets plow through the surrounding molecular cloud, they create beautiful structures called Herbig-Haro objects, glowing knots and streamers of gas, that mark the jet's passage through space. These objects, visible in optical telescopes as colorful nebular emissions, provide direct evidence of the star formation process and allow astronomers to study the properties of protostellar jets in detail. Like whispers in the night, the protostar communicates its presence through its infrared emission. To cool to shine brightly in visible light, it glows warmly in the infrared, fed by the accretion energy and the slow gravitational contraction of its interior. This infrared emission can penetrate the dusty cocoon that still surrounds many protostars, allowing us to study stellar birth even when the object remains hidden from optical view. The protostar spectrum tells us about its temperature, mass, and evolutionary state. As it evolves, its surface temperature gradually increases while its luminosity may actually decrease, following a complex evolutionary track. Through the Hertzsprung-Russell diagram, the fundamental chart that relates stellar temperature to luminosity. These tracks, computed using sophisticated models of stellar structure and evolution, allow astronomers to determine the age and mass of protostars from their observed properties. In the quiet space surrounding the protostar, the disk begins to show signs of further evolution. Temperature and pressure gradients within the disk create conditions suitable for the condensation of different materials at different distances from the central object. Close to the protostar, where temperatures exceed 1000 degrees Kelvin, only the most refractory materials, metals and rocks, can exist in solid form. Further out, beyond the water-ice line, frozen volatiles begin to condense, dramatically increasing the amount of solid material available for planet formation. The protostar's magnetic field plays a crucial role in regulating both accretion and the dispersal of the birth cloud. Strong magnetic fields can link the protostar to the inner edge of the accretion disk, forcing the disk material to rotate with the star and preventing accretion until the magnetic coupling is broken. This process, called magnetic braking, may explain why some protostars appear to have very slow rotation rates, despite accreting material with significant angular momentum. As our journey continues through this phase of stellar evolution, we observe that protostars come in a variety of masses and evolutionary states. The most massive protostars evolve more rapidly, reaching higher temperatures and luminosities during their pre-main sequence phase. These objects may clear away their birth cocoons relatively quickly, emerging as visible T-Tauri stars, young stellar objects that are still contracting toward the main sequence, but no longer deeply embedded in dusty envelopes. Lower-mass protostars evolve more slowly and may remain embedded in their dusty cocoons for much longer periods. These objects, often called Class I sources in the infrared classification scheme, bridge the gap between the earliest phases of star formation and the more evolved T-Tauri phase. Their study provides crucial insights into how stellar masses are determined and how the stellar initial mass function. The distribution of stellar masses at birth is established. Let us drift into the most profound moment in a star's life, the ignition of nuclear fusion in its core. After millions of years of patient gravitational contraction, the protostar's center finally reaches the critical conditions needed to begin the nuclear reactions that will power it for billions of years to come. This moment marks the true birth of a star, the transition from a gravitationally contracting object to a self-sustaining nuclear reactor. The conditions required for fusion are extreme by any earthly standard, yet they rise naturally through the gentle persistence of gravity. In the star's core, temperatures must exceed 10 million degrees Kelvin, hot enough that atoms are completely stripped of their electrons, creating a plasma of bare nuclei and free electrons. The density must be enormous, with matter compressed to more than 10 times the density of lead, creating conditions where atomic nuclei are forced into close proximity. Despite their mutual electrical repulsion, Now we float toward the quantum mechanical heart of stellar energy production, where the fundamental forces of nature orchestrate the transformation of hydrogen into helium. This process, called nuclear fusion, requires hydrogen nuclei, simple protons, to overcome their electrical repulsion and approach close enough for the strong nuclear force to bind them together. Under normal circumstances, this would be impossible, as the electrical repulsion is far stronger than the thermal energy available, even at stellar core temperatures. But quantum mechanics provides a pathway through quantum tunneling, a phenomenon where particles can pass through energy barriers that would be insurmountable in classical physics, even though most protons lack the energy to overcome electrical repulsion directly. A small fraction can tunnel through the barrier and fuse together. This process is incredibly rare for any individual proton, but with countless billions of collisions occurring every second in stellar cores, fusion proceeds at exactly the rate needed to balance gravitational collapse. In the quiet space of the stellar core, hydrogen fusion follows a chain of reactions known as the proton-proton chain. First, the protons fuse to form a deuteron-heavy hydrogen, with one proton converting to a neutron through beta-plus decay, releasing a positron and a neutrino. The deuteron then fuses with another proton to form helium-3, releasing a gamma-ray photon. Finally, the helium-3 nuclei fuse to form helium-4, returning two protons to the mix and completing the cycle. Gently, we discover that this fusion process is remarkably efficient at converting matter directly into energy according to Einstein's famous equation E equals mc. Each helium nucleus weighs slightly less than the hydrogen nuclei from which it formed, and this missing mass is converted entirely into energy. Though the mass difference is tiny, less than 1%, the speed of light squared is so large that even this small conversion releases enormous amounts of energy. The energy released by fusion takes many forms, but primarily gamma-ray photons and neutrinos. The neutrinos, having virtually no interaction with matter, escape immediately from the stellar core and stream out into space at the speed of light, carrying with them direct information about the nuclear reactions in the star's heart. The gamma-ray photons, however, begin a much longer journey to the surface. As our journey continues outward from the fusion core, we follow the path of these energetic photons as they begin their migration toward the stellar surface. In the dense stellar interior, photons cannot travel far before being absorbed and ray-emitted by atoms in the plasma. This creates a random warp process where each photon scatters countless times, gradually working its way outward while losing energy with each interaction. This journey from core to surface is extraordinarily long, not in distance but in time. While the straight-line distance might be only a few 100,000 kilometers, the random warp process means that photons may take anywhere from thousands to millions of years to finally escape into space. The photons we see from the Sun today began their journey in the solar core during the last ice age, or even earlier in human prehistory. Like whispers in the night, the energy from fusion gradually transforms as it moves outward through the stellar interior. The high-energy gamma rays from the core are repeatedly absorbed and ray-emitted at progressively lower energies, eventually emerging as the visible light and other radiation we observe from stellar surfaces. This process naturally regulates the star's energy output, creating a stable fusion reactor that can burn steadily for billions of years. The onset of nuclear fusion marks the beginning of what astronomers call the main sequence phase of stellar evolution. Once fusion ignites, it provides exactly the energy needed to support the star against gravitational collapse, creating a state of hydrostatic equilibrium. The outward pressure from radiation and hot gas balances the inward pull of gravity, maintaining the star at a stable size and temperature for the vast majority of its life. In the quiet space of this equilibrium, stars settle into a remarkably stable configuration. The fusion rate automatically adjusts to provide exactly the energy needed to maintain the balance. If the core contracts slightly due to cooling, the temperature and density increase, speeding up fusion reactions and providing more energy to halt the contraction. If the core expands due to excess heating, fusion slows down, allowing the core to cool and contract back to equilibrium. This self-regulating mechanism, called the stellar thermostat, is one of the most elegant examples of negative feedback in nature. It allows stars to maintain stable energy output over timescales that span significant fractions of the age of the universe. Our Sun, for example, has been burning steadily at nearly its current rate for over 4 billion years, and will continue to do so for another 5 billion years. Now we float toward the different fusion pathways that operate in stars of different masses. In stars like our Sun, with core temperatures around 15 million degrees, the proton-proton chain dominates hydrogen burning. But in more massive stars, where core temperatures exceed 20 million degrees, an alternative pathway called the CNS cycle becomes more important. This process uses carbon, nitrogen, and oxygen nuclei as catalysts to convert hydrogen to helium more efficiently. The CNS cycle's temperature dependence is much steeper than that of the proton-proton chain, making massive stars far more luminous than their lower-mass counterparts. A star with 10 times the Sun's mass may shine with thousands of times the Sun's luminosity, burning through its nuclear fuel much more rapidly and living a correspondingly shorter life. Gently, we discover that the ignition of fusion also marks the beginning of stellar nuclear synthesis, the process by which stars create the heavier elements that make planets and life possible. While hydrogen burning only produces helium, more advanced fusion processes in massive stars can create elements up to iron. In the periodic table, these elements are eventually dispersed into space when stars die, enriching the interstellar medium for future generations of star formation. The transition from protostar to main sequence star is often accompanied by dramatic changes in the object's appearance and behavior. The onset of fusion may trigger powerful stellar winds that blow away the remaining birth cocoon, revealing the newborn star in visible light for the first time. Young stars may also show violent flaring activity as their magnetic fields readjust to the new equilibrium conditions. As our journey continues through this crucial phase of stellar evolution, we observe that the time required to reach the main sequence depends strongly on stellar mass. The most massive stars may take only a few 100,000 years to ignite fusion, while the lowest mass stars may require hundreds of millions of years to reach the necessary core conditions. This means that we can observe stars at all stages of pre-main sequence evolution in nearby star-forming regions. Now we float towards some of the most magnificent stellar nurseries in our galaxy, where the processes we've been exploring play out on grand scales across regions, spanning hundreds of light years. These star-forming regions are among the most beautiful and scientifically important objects in the night sky, offering laboratories where we can study stellar birth in extraordinary detail. The Orion Nebula, perhaps the most famous stellar nursery of all, lies just 1,500 light-years from Earth in the constellation Orion, visible to the naked eye as the middle star in Orion's sword. This glowing cloud of gas and dust is actually a vast stellar maternity ward, where new stars are being born at this very moment. The nebula spans about 25 light-years and contains enough material to form thousands of new stars. In the quiet space of the Orion Nebula, we can observe the entire stellar birth process in a single field of view. The trapezium cluster at the nebula's heart contains several massive, hot young stars whose intense ultraviolet radiation illuminates the surrounding gas, creating the beautiful glowing colors we see in photographs. These stars are only a few million years old, mere infants by stellar standards, yet already they are beginning to disperse the cloud from which they formed. Let's drift into the infrared view of Orion, where dust-enshrouded protostars become visible as bright sources of heat radiation. The Kleinman Low Nebula, hidden behind thick dust clouds in visible light, reveals itself as one of the most active star-forming regions in our galactic neighborhood. Here, massive protostars are still growing through accretion, their powerful jets carving cavities in the surrounding molecular cloud. The Orion Molecular Cloud Complex extends far beyond the visible nebula, encompassing a vast network of dark molecular clouds, where the earliest stages of star formation are occurring. These dark clouds, visible as silhouettes against the background stars, contain the cool, dense gas needed for gravitational collapse. Within them, astronomers have identified hundreds of young stellar objects at various evolutionary stages. As our journey continues to other stellar nurseries, we encounter the Eagle Nebula, home to the famous pillars of creation, towering columns of dense gas and dust that resist the erosive effects of nearby hot stars. These pillars, stretching several light-years in length, are stellar nurseries in their own right, with new stars forming within their dense cores even as their surfaces are sculpted by stellar winds and radiation. Gently, we discover that the pillars represent a beautiful example of triggered star formation, where the birth of one generation of stars influences the formation of the next. The hot, massive stars that illuminate the Eagle Nebula also create shock waves and compression fronts that can trigger gravitational collapse in nearby molecular clouds. This creates a chain reaction of stellar birth that propagates through the star-forming region. Over millions of years, the Carina Nebula, located in the southern sky, hosts some of the most massive and luminous stars known. This stellar nursery spans over 300 light-years and contains several star clusters with different ages, showing us how star formation proceeds in waves across large molecular cloud complexes. The nebula's most famous resident is Eta Coronae, a hypergent star that underwent a dramatic eruption in the 19th century and remains one of the most massive and unstable stars in our galaxy. Now we float toward the Rosette Nebula, where a central cavity carved out by stellar winds and radiation pressure creates a beautiful, ring-like structure. The molecular cloud surrounding this cavity continues to form new stars, particularly along the dense rim where the expanding bubble compresses the gas. This represents another example of how stellar feedback, the influence of existing stars on their environment, shapes ongoing star formation. In the quiet space of these stellar nurseries, we observe that star formation is not a random process but follows predictable patterns. Related to the structure and dynamics of molecular clouds, stars tend to form in clusters and associations, with the most massive stars typically found at the centers of these groupings. This clustering reflects the hierarchical structure of the parent molecular clouds, which themselves contain dense cores and filaments where star formation preferentially occurs. Like whispers in the night, RADIO observations reveal the hidden structure of molecular clouds through the emission of carbon monoxide and other molecules. These observations show that star-forming regions have complex velocity structures, with turbulent motions and organized flows that influence where and when stars form. The interplay between turbulence, magnetic fields, and gravity creates the beautiful complexity we observe in stellar nurseries. The study of stellar nurseries has been revolutionized by multi-wavelength astronomy, combining observations from radio telescopes that probe molecular gas, infrared telescopes that penetrate dust clouds, and X-ray observatories that reveal the hot plasma associated with young stellar objects. Each wavelength tells a different part of the story, and only by combining them all can we develop a complete picture of the star formation process. As our journey continues through these cosmic maternity wards, we observe that different stellar nurseries show different characteristics, depending on their local environment. Nurseries located in the dense spiral arms of galaxies tend to form more massive stars and larger clusters, while those in the galactic halo or between spiral arms form primarily low-mass stars. This environmental dependence helps explain the observed variations in stellar populations across different types of galaxies. The nearest star-forming regions to Earth provide unique laboratories for studying stellar birth in unprecedented detail. The Taurus Auriga complex, located only 450 light-years away, allows astronomers to study individual protostars and pre-main sequence stars with exquisite precision. The relatively sparse stellar density in this region means that we can follow the evolution of individual objects without the confusion that arises in more crowded stellar nurseries. Gently, we discover that stellar nurseries are not permanent features, but rather transient phenomena in galactic evolution. The massive stars they produce live only a few million years before exploding as supernovae, dispersing heavy elements into the interstellar medium and potentially triggering new episodes of star formation in nearby molecular clouds. This creates a cycle of stellar birth, death, and rebirth that has continued throughout the history of our galaxy. The dispersal of stellar nurseries by their own stellar offspring represents a natural regulatory mechanism that prevents star formation from proceeding too rapidly. Without this feedback, galaxies might convert all their gas into stars very quickly, ending star formation entirely. Instead, the balance between star formation and stellar feedback maintains a steady rate of stellar birth that can continue for billions of years. Recent observations with the Hubble Space Telescope and other advanced instruments have revealed that many stellar nurseries contain brown dwarfs, objects too massive to be planets, but too small to sustain nuclear fusion. These failed stars provide important clues about how the stellar mass function is established, and what determines the minimum mass needed for stellar ignition. Like whispers in the night, many secrets of star formation remain hidden from our current understanding, representing some of the most fascinating unsolved problems in modern astrophysics. Despite decades of observations and theoretical work, fundamental questions about how stars form continue to challenge astronomers and drive new research. Across the electromagnetic spectrum, one of the deepest mysteries concerns the stellar initial mass function, the distribution of masses that newborn stars possess. Observations consistently show that most stars are born with relatively low masses, similar to or smaller than our Sun, while very massive stars are extremely rare. This mass distribution appears to be nearly universal, showing remarkably similar patterns in star-forming regions throughout our galaxy, and in other galaxies as well. In the quiet space of theoretical astrophysics, scientists have proposed numerous mechanisms to explain this mass function, from the fragmentation of turbulent molecular clouds to the competitive accretion of protostars in dense clusters. Yet no single theory can fully account for the observed distribution and the physical processes that determine stellar masses during the formation process remain poorly understood. The formation of the most massive stars presents particular challenges to our understanding. These stellar giants, containing tens or even hundreds of times the mass of our Sun, face a fundamental problem during their formation as they grow through accretion. Their increasing luminosity creates radiation pressure that should blow away the infalling material, halting further growth long before they reach their observed masses. Gently, we discover that several proposed solutions to this massive star formation problem involve complex, three-dimensional processes that are difficult to model computationally. Accretion through equatorial disks might allow material to reach the protostar, while avoiding the strongest radiation pressure along the polar directions. Alternatively, massive stars might form through the collision and merger of smaller protostars in dense cluster environments. Now we float toward another persistent mystery, the role of magnetic fields in star formation. Observations indicate that molecular clouds are threaded by magnetic fields that may significantly influence how they collapse and fragment. These fields could provide additional support against gravitational collapse, regulate the rate of star formation, or channel material flows during the accretion process. However, measuring magnetic fields in star-forming regions is extremely challenging, requiring specialized techniques such as polarimetry of starlight or radio observations of molecular line emission. The limited observational data we have suggests that magnetic fields are indeed important, but their detailed role in the star formation process remains largely theoretical. The question of how binary and multiple star systems form represents another major unsolved problem, since most stars are members of binary or multiple systems. Understanding their formation is crucial for a complete theory of stellar birth. Do binary stars form through the fragmentation of a single collapsing core, the capture of one star by another, or the evolution of initially single protostars in dense cluster environments? As our journey continues through these unsolved mysteries, we encounter the puzzle of brown dwarfs, objects that straddle the boundary between stars and planets. These failed stars have masses too low to sustain hydrogen fusion in their cores, yet they appear to form through processes similar to normal stellar formation. Understanding why some collapsing cores become brown dwarfs while others become stars could provide crucial insights into the physics of stellar birth. The relationship between star formation and planet formation remains another area of active research. We now know that planets are common around other stars, but the detailed processes that lead from dusty protostellar disks to fully formed planetary systems are still being worked out. How do dust grains grow into planets? What determines whether a system forms terrestrial planets, gas giants, or both? How do planetary system architectures relate to the initial conditions in protostellar disks? Like whispers in the night, observations of protoplanetary disks around young stars are beginning to reveal the early stages of planet formation. Rings, gaps, and spiral structures in these disks suggest that planets may form much earlier than previously thought, perhaps while the central star is still accreting material. However, connecting these early signatures to the mature planetary systems we observe around older stars remains a significant challenge. The influence of stellar feedback on star formation represents another frontier of current research. How do the winds, radiation, and eventual supernova explosions of massive stars affect ongoing star formation in their vicinity? Can stellar feedback trigger new episodes of star formation through compression of nearby molecular clouds? Or does it primarily serve to suppress further stellar birth by dispersing the available gas? In the quiet space of galaxy evolution, these feedback processes may be crucial for understanding how galaxies regulate their star formation rates over cosmic time. Observations show that the rate of star formation in the universe has declined significantly since its peak about 10 billion years ago, and stellar feedback likely plays a major role in this cosmic evolution. The formation of the first stars in the universe, population 3 stars, that formed from primordial gas containing only hydrogen and helium, presents unique challenges that we are only beginning to address. Without heavy elements to provide cooling and dust grains to facilitate chemical reactions, the first molecular clouds must have behaved very differently from those we observe today. These first stars were likely much more massive than typical modern stars, and their eventual deaths as supernovae began the process of chemical enrichment that made later generations of star formation possible. Gently, we discover that many of these mysteries are interconnected, with advances in one area potentially illuminating others. The development of increasingly sophisticated computer simulations, combined with observations from next-generation telescopes, promises to revolutionize our understanding of star formation in the coming decades. The Atacama Large Millimeter, Submillimeter Array ALMA has already begun to transform our view of protostellar disks and star-forming regions, providing unprecedented resolution and sensitivity for observations of molecular gas and dust. Future facilities like the extremely large telescopes will allow direct imaging of exoplanets around nearby young stars, potentially revealing planet formation in action. As our journey continues through these unsolved problems, we appreciate that the mysteries of star formation connect to some of the deepest questions in astrophysics and cosmology. Understanding how stars form is essential for comprehending galaxy evolution, the chemical enrichment of the universe, and ultimately the conditions that led to the emergence of life on Earth. The search for answers to these questions drives astronomers to develop new observational techniques, build more powerful telescopes, and create increasingly sophisticated theoretical models. Each new discovery raises new questions, ensuring that the study of star formation will remain an active and evolving field of research for generations to come. In the quiet space of cosmic contemplation, we come to understand that the story of star formation is ultimately our own story, written in the nuclear furnaces of distant suns, and recorded in the very atoms that compose our bodies. Every element heavier than hydrogen and helium, the carbon in our DNA, the oxygen we breathe, the calcium in our bones, the iron in our blood, was forged in the core of a star that lived and died before our sun was born. This profound connection between stellar nuclear synthesis and biological existence represents one of the most beautiful insights in modern science. We are not merely observers of the cosmic drama, but active participants, living embodiments of stellar evolution, carrying the products of ancient fusion reactions in every cell of our bodies. As Carl Sagan so eloquently expressed, we are made of star stuff, and our connection to the cosmos runs deeper than metaphor. As our journey continues through this cosmic perspective, we trace the path of elements from stellar cores to living organisms. Let's drift into the grand cycle that connects stellar death to new star formation and, ultimately, to the emergence of life. When massive stars exhaust their nuclear fuel, they explode as supernovae, dispersing their newly created elements into the interstellar medium. These stellar explosions enrich the galactic gas with heavy elements, providing the raw materials needed to form planets and, eventually, complex chemistry and biology. The shock waves from supernovae also compress nearby molecular clouds, triggering new episodes of star formation in a beautiful example of how stellar death begets stellar birth. This process has continued for billions of years, gradually increasing the heavy element content of the galaxy and creating the conditions necessary for the formation of planetary systems capable of supporting life. Now we float toward the realization that star formation has evolved dramatically. Over the history of the universe, the first stars, formed from primordial gas containing only hydrogen and helium, were likely much more massive than typical stars today. These population 3 stars lived brief, violent lives before exploding as supernovae or collapsing into black holes, beginning the process of chemical enrichment. Subsequent generations of stars formed from increasingly metal-rich gas, allowing the formation of dust grains and the efficient cooling processes that characterize modern star formation. This chemical evolution has proceeded at different rates in different parts of the universe, creating a complex tapestry of stellar populations with varying compositions and formation histories. Gently, we discover that our Sun and solar system represent a particular moment in this cosmic evolution, forming about 4.6 billion years ago from gas that had already been enriched by billions of years of stellar nuclear synthesis. The heavy elements present in the solar nebula allowed the formation of rocky planets like Earth and provided the chemical diversity necessary for the emergence of life. The timing of our Sun's formation was crucial for the development of life as we know it. If our solar system had formed much earlier in galactic history, it might have lacked the heavy elements needed for rocky planet formation. If it had formed much later, the declining rate of star formation in the universe might have made suitable conditions increasingly rare. In the quiet space of astrobiological speculation, we consider how star formation processes might influence the distribution of life throughout the universe. The formation of planetary systems appears to be a natural consequence of star formation, with most young stars showing evidence of circumstellar disks that likely evolve into planetary systems. This suggests that planets, and potentially life, might be common byproducts of stellar birth. However, the conditions suitable for life as we know it may require specific circumstances during star formation. The star must be neither too massive leading to a short lifetime nor too small, providing insufficient energy for complex chemistry. The planetary system must form with the right architecture to allow stable orbits. In the habitable zone, the host galaxy must have undergone sufficient chemical evolution to provide heavy elements while avoiding excessive radiation from supernova explosions or active galactic nuclei, like whispers in the night. The search for life on other stars has become one of the most exciting frontiers in astronomy. The discovery of thousands of exoplanets, many in potentially habitable orbits around their host stars, suggests that the products of star formation may indeed be conducive to biological evolution. Future observations may reveal biosignatures in the atmospheres of these distant worlds, confirming that star formation has led to life in multiple locations throughout the galaxy. As our journey continues through this cosmic perspective, we appreciate that star formation is not merely a local phenomenon but a fundamental process that shapes the evolution of galaxies themselves. The rate at which galaxies convert their gas into stars determines their appearance, chemical composition, and ultimate fate. Galaxies that form stars to rapidly exhaust their gas supplies and fade into red. Elliptical systems, those that form stars to slowly may never develop the chemical complexity needed for planet formation. The feedback between star formation and galactic evolution creates a complex web of interactions that astronomers are still working to understand. Supermassive black holes at galactic centers can regulate star formation through powerful outflows, while mergers between galaxies can trigger bursts of stellar birth. These processes connect the physics of individual star formation to the large-scale structure of the universe itself. Now we float toward the future of star formation in our own galaxy and throughout the universe. The Milky Way continues to form new stars, though at a much slower rate than in its youth. Our galaxy converts only a few solar masses of gas into stars each year, compared to rates that may have been 10 times higher in the past. This declining star formation rate reflects both the consumption of available gas and the increasing efficiency of stellar feedback in preventing further collapse. On cosmic timescales, star formation throughout the universe is also declining as the expansion of space dilutes the density of matter and makes gravitational collapse increasingly difficult. The peak era of star formation occurred roughly 10 billion years ago, and we now live in a universe where stellar birth is becoming increasingly rare. Future generations of astronomers may inhabit a cosmos where star formation has largely ceased, leaving only the slowly cooling remnants of today's stellar population. Gently, we discover that this cosmic perspective imbues star formation with profound meaning beyond its scientific significance. The processes that create stars also create the conditions for complexity, chemistry, and ultimately consciousness to emerge in the universe. Without star formation, the cosmos would remain a cold, dark expanse of hydrogen and helium, devoid of the rich chemistry that makes planets, life, and intelligence possible. Our ability to understand and appreciate star formation represents a remarkable achievement of cosmic evolution. The universe has become conscious of itself through the emergence of intelligence on at least one planet orbiting one star in one galaxy among billions. Through our scientific investigations, we participate in the universe's own journey of self-discovery, using instruments and methods that are themselves products of stellar nuclear synthesis to understand the processes that created us. In the quiet space of this cosmic meditation, we recognize that studying star formation is ultimately an act of cosmic introspection. We are the universe examining its own creative processes, using minds made of star stuff to understand how stars form and evolve. This reflexive quality of cosmic consciousness represents perhaps the most profound mystery of all: how the laws of physics that govern stellar birth have led, through billions of years of evolution, to observers capable of comprehending their own cosmic origins. As we prepare to conclude our gentle journey through the stellar nurseries of the cosmos, we carry with us not only scientific knowledge, but also a deeper appreciation for our place in the grand story of cosmic evolution. We are connected to every star that shines in the night sky through the common physics that governs stellar birth and through the nuclear processes that created the elements of our existence. In understanding how stars form, we glimpse the mechanisms through which the universe creates complexity, beauty, and ultimately the conditions for life itself. As our peaceful journey through the stellar nurseries of the cosmos draws to its close, we find ourselves gently returning to our small blue planet, carrying with us the profound knowledge of how stars are born from whispers of gas and dust in the vast cosmic ocean. Tonight, as you drift towards sleep, you can look up at the night sky with new understanding, knowing that each point of light represents a successful completion of the remarkable process we've explored together. In the quiet space of your dreams, remember that star formation continues at this very moment throughout our galaxy and beyond. In distant molecular clouds, gravity is slowly gathering matter together, beginning the patient process that will, millions of years from now, result in new suns shining in the cosmic dark. These future stars will warm new worlds and perhaps foster new forms of life, continuing the grand cycle of cosmic evolution that connects us all to the stars above. The story of star formation is ultimately a story of hope and continuity, written in the language of physics across time scales that dwarf human experience, yet result in the very conditions that make our existence possible. From the gentle collapse of molecular clouds to the ignition of nuclear fusion, from the dispersal of stellar nurseries to the enrichment of the galaxy with heavy elements, each step in the stellar birth process contributes to the ongoing evolution of our universe toward greater complexity and beauty. Like whispers in the night, the secrets of star formation continue to unfold through the dedicated work of astronomers and astrophysicists around the world. Each new observation, each theoretical insight, each computational simulation brings us closer to understanding the full beauty and complexity of how stars form. Yet even as our knowledge grows, new mysteries emerge, ensuring that the cosmic story of stellar birth will continue to inspire wonder and discovery for generations to come. As you settle into peaceful sleep tonight, carried gently by the cosmic winds of understanding we've shared, remember that you are intimately connected to this grand process of stellar birth and evolution. The atoms in your body were forged in stellar cores, dispersed by stellar winds and supernova explosions, and eventually incorporated into the molecular cloud that gave birth to our sun and solar system. You are both a product of past star formation and a witness to its ongoing continuation throughout the universe. In your dreams, you might drift once more through the stellar nurseries. We've revisited together the glowing clouds of the Orion Nebula, the towering pillars of the Eagle Nebula, the vast complexes where new stars take their first breath in the cosmic dark. These magnificent regions represent more than mere astronomical objects. They are the cosmic gardens where the seeds of future worlds are planted and nurtured by the patient forces of physics. The gentle processes we've explored tonight, gravitational collapse, nuclear fusion, stellar feedback, and chemical enrichment, operate according to natural laws that are both elegant and profound. In their mathematical beauty, we glimpse the deeper harmonies that govern cosmic evolution, the subtle balances that allow complexity to emerge from simplicity, and life to flourish in an otherwise vast and empty universe. As the night deepens around you and sleep draws near, carry with you the peaceful knowledge that star formation represents one of nature's most beautiful achievements, the transformation of primordial gas into shining beacons of light and warmth that can sustain life across cosmic time. This process, playing out in countless regions throughout the observable universe, ensures that our cosmos remains a dynamic, evolving, and ultimately life-giving environment. The mysteries that remain in our understanding of star formation, the questions about massive star formation, the role of magnetic fields, the origins of planetary systems, and the emergence of life itself, represent not gaps in our knowledge but opportunities for future discovery and wonder. Each unsolved problem is an invitation to deeper understanding, a doorway to new insights about the cosmos and our place within it. Tonight, as you rest peacefully under the gentle light of stars, born through the processes we've explored together, remember that you are participating in one of the universe's greatest achievements, the emergence of consciousness capable of understanding its own cosmic origins. Through your dreams and contemplations, the universe continues its journey of self-discovery, using minds made of star stuff to comprehend the stellar processes that created them. Good night from the sleepy scientist.